We know that every separable Hilbert space has an orthonormal basis, so an actual question is to ask, is it true that every separable Banach space has a shadow basis? Now the answer to that question turns out to be no. It's a very famous result of Perrin-Flo in 1973 answering that problem of Banach. So we won't see the counterexample that Perrin-Flo created. We will just see a result due to Mazur, which is a much more basic partial answer to that question. And the result we will see is theorem 10.5. It says that every infinitesimal Banach space may not have a basis, but it will always have what's called a basic sequence. Now, what's a basic sequence? Well, it's definition 10.4, a sequence that is a basis of the closure of its span. So if you go back to proposition 10.3, what this is saying is that we can always find a sequence that satisfies property 1 and satisfies property 3 from proposition 10.3, but it may fail part 2. But at least in the closure of that span, which may not be the whole space, we do have a basis. So let's prove the theorem. And in order to do that, we will first prove a lemma. And the lemma is the following. So this is true in every infinite dimensional Banach space. And you look at a finite dimensional subspace and you're going to be able to find a certain direction such that when you add vectors in that direction to any vector in your finite dimensional space, you don't increase their norm particularly much. So let's prove this lemma first. Okay, so let's give ourselves an epsilon. And we have a subspace Y that is finite dimensional. Now, since the subspace is finite dimensional, its unit sphere has to be compact. Okay, so if it's compact, I can cover it with a finite cover using open sets. So I have that there exists a sequence Yj in the unit sphere of Y, and that is such that for every Y in the unit sphere, there exists a J between 1 and n, such that Y is close enough to Yj, and let's make close enough epsilon over 2. We'll see that this is neater than if I take epsilon at this stage. Okay, so I have these elements that provide the center of balls covering my unit sphere of Y, and by Banach, I can find norming functionals for this Yj. So there exist Yj stars, and they're going to be in the unit ball of X star, and they will be such that Yj star applied to Yj is equal to, well, the norm of Yj, which is 1 for all j between 1 and capital N. Okay, now I only have finitely many of them, so one thing for sure is that they cannot possibly span the entire dual because my Banach space to start with is infinite dimensional. So this cannot be X star. Okay. Now, I'm also claiming that the intersection of the kernel of the Yj star cannot be trivial. So this is a remark here. If the intersection of the kernel of the Yj star is 0, okay, then we have that it has to be inside the kernel of Y star for any Y star in the in X star, well, non-zero, so let's say in the unit sphere of X star. Right, but if that happens, we have, as we've seen before, by an application of Banach in this geometric form, when we have these intersections of kernels, you can prove that Y star has to belong to the closure of the span of the Yj star. And that will be a contradiction. Okay, so the intersection of these kernels cannot be trivial. So there exists an X, non-zero. Okay, there exists an X, that is in the intersection of all this kernel, and it's non-zero, so I can renormalize it and so make it in the intersection of this kernel intersected with the unit sphere of x. And now that x is going to give me the appropriate direction. So now I'm going to pick a y in capital Y that has norm 1, let's say. So let's pick it in the unit sphere to start with. And then I'm going to pick a lambda real. And then I'm going to choose the j between 1 and n, for which y minus yj is smaller than epsilon over 2 because of my compactness argument to start with. And now I have to compute the norm of lambda x plus y and show that this is greater than 1 upon 1 plus epsilon times the norm of y. So what can I say about this? Well, I can use triangle inequality and say this is greater than lambda x plus yj minus y minus yj. Okay, and that is greater than lambda x plus yj tested on yj star, of course, because the norm is defined as a soup testing on all functionals in Sx star, and yj star is only one of them. And then this y minus yj is at worst epsilon over 2. So I have this inequality. And this inequality now, you have to remember that x is in the kernel of all the yj star. So lambda x times yj star, or duality product with yj star, is 0. So what we get here is yj tested on yj star minus epsilon over 2, and this has been designed to be 1. So we get that this is greater or equal to 1 minus epsilon over 2. And 1 minus epsilon over 2, well, you can do a little computation. This is greater than 1 upon 1 plus epsilon times the norm of y, because I've chosen the norm of y to be 1. And so, okay, so once you have that, it's just a matter of doing a little scaling. You then get that for every y in capital Y, lambda x plus y divided by norm of y is greater than, say, multiplied by 1 plus epsilon is greater than 1, and that's true for every lambda. And so you get that 1 plus epsilon lambda times norm of y times x plus norm of y is, sorry, plus y, not norm of y, is greater than norm of y. And of course you could pick your new lambda to be the old lambda divided by norm of y. And so this gives the result, which proves the lemma. Okay, we can now prove theorem 10.5, the existence of a basic sequence using lemma 10.6 and proposition 10.3 actually. So the way we do that is inductive. We just pick a first element for our basis, E1, in the unit sphere of x, so it has norm 1, and then given some epsilon 1, what we do is we use the lemma 10.6, and with the lemma, what can we do? We can find a vector E2 in the unit sphere of x such that for all lambda 1, lambda 2 in R, lambda 1 E1, an element of the one-dimensional space generated by E1, is smaller or equal than 1 plus epsilon 1 times lambda 1 E1 plus lambda 2 E2, right? We add this direction x, which is E2 here, to the one-dimensional subspace Y, which is the span of E1. Okay, now you can iterate that, and iterating that argument, so now we're going to find, a direction that's such that we are reasonably close to any vector in the span of E1, E2. And then you keep doing that, and you can pick a whole family En, n equal 1 to capital N, in Sn, such that what? Such that for every sequence of real lambda j equal 1 to n, we have that the sum of lambda j ej up to n minus 1, capital N minus 1, is smaller than 1 plus epsilon times the sum j equal 1 to capital N of lambda j ej, epsilon n capital N. Okay, and we can do that for a whole sequence of epsilon. So at the very beginning I should have said, rather than just take one epsilon that I need for the first step, here I should take a whole sequence of epsilons. So a whole sequence in R plus, and I'm going to just choose them small enough eventually. So now what happens is that you keep iterating that, and you get that for all capital N and capital M in N, with n greater than m, you can say that the sum j equal 1 to capital M of lambda j ej is smaller than the product of the 1 plus epsilon j running between, between m and n, times the sum lambda j ej j equal 1 to n. Just repeating the step star, capital N minus capital M times. Okay, and we can do that for any choice of sequence epsilon n. So now, choosing epsilon n such that the product of 1 plus epsilon j equal 1 to infinity, we want this infinite product to converge, and we're going to make it smaller than 2, let's say. Then if we've done that, then we have that the norm of En is 1 for all n in n, and the fact that the sum of lambda j ej equal 1 to m is smaller than 2 times the sum of lambda j ej equal 1 to n, and that is true for every n m in n greater than m, and for every sequence lambda j equal 1 to n in R to the n. So we've checked property 1 in proposition 10.3 here, and we've checked property 3 in proposition 10.3 here. So because property 2 is automatically verified on the closure of the span of the EJs, then we have that the EJs form a basic sequence. That is to say, they satisfy the assumptions of 10.3, not on the full space, but on the closure of the span of those EJs that I've created using lemma 10.6 repeatedly. And that proves theorem 10.5. So we may not have a basis in every separable Banach space, but at the very least we have a basic sequence.